Good afternoon, everybody. Thank you for coming to the last session at RedisConf. My name is Jiaqi Wang. I am a software developer on the owner engagement team at Redfin. So today I'm going to be talking about serving automated home valuation with Redis and Kafka. Redfin is a technology-powered real estate brokerage. We not only serve home information as a platform, but also employ real estate agents to provide professional home buying and selling services. Every month, over 22 million users come to Redfin to check out homes across the country, to find out how much their home is worth, to keep updated with the neighborhood trend, as well as to get in touch with a professional real estate agent for services. And as far as owner engagement team, we mostly focus on homeowner experiences, providing tools to help homeowners understand their home value better, as well as to keep their home information up to date. In terms of Redis, Redfin adopted Redis since 2016, and the open source version has been serving us well. We use the Redis client, because in the backend we use Java a lot. And we have one multi-tenant cluster in prod, as well as several feature nodes as standalone nodes. We have two primary use cases for Redis, one as an RRU cache, another as a rate-limiting tool to detect malicious activity during user registration, as well as email sharing and some other scenarios. So last year, my coworker, Robert Gay, came to Redis conference and presented our thoughts about possible use cases of Redis from a high level. And this year, I'm going to be focused on a specific use case at Redfin and go through our thought process of designing the architecture around it, and more specifically, a cache warm-up pipeline powered by Kafka and Samza. This is our agenda today. First, I'm going to talk about feature overview. Next, go through the design iterations. After that, we'll do a deep dive into the cache warm-up. And lastly, talk about next steps. So what is automated home valuation, or what we call Redfin estimate? It is a calculation of the market value of an individual home, or basically what we think your home is worth. Recently, we have commissioned analysis that shows Redfin estimate is the most accurate on the market. If you have been a Redfin user, you've probably already seen it on the home details page on our website, or inside our mobile apps. We also use it extensively in our email services, internal tools for agents, as well as in a fairly new experiment that we're running in a couple markets called Redfin Now, which is a product that tries to buy homes directly from our customers, and the value we pay for the home largely depends on the Redfin estimate value. One more place you will see the Redfin estimate value is on the map page when you zoom in enough. And we will show estimate values for nearby homes that are not currently on the market for sale. I personally like this feature a lot because it gives you a good idea on the overall home prices in a given neighborhood, not because I would like to stalk my neighbors. But different from the other use cases, the specific usage presents some unique technical challenge for us that I'll dive into later in this talk. Onto design iterations. So coming back, this was our stack before we fitted a cache layer into our system. So on your right side, we have an estimate API set up on AWS behind the Amazon API gateway, serving raw estimate value on the left. Actually, which way? On the left side, we have the web server in the middle. Each of the boxes represents a specific service or feature that requires the estimate data. And as you could see, each of the boxes is also responsible for reaching out to the database to hydrate the data. There have been a couple issues we've seen about this specific design. First, due to the complex nature of the estimate data itself and the fact that a property can be represented in many different forms, the estimate API takes multiple parameters. And as developers, we all know when there is a complicated API, we're kind of asking for trouble. So in our specific case, this specific API, sometimes it is possible for it to return a different estimate even for the same home, depending on the kind of parameters get passed in. So for example, say the user receives a home report, which is a monthly email we send out to the users, notifying them how much their home value has updated in the past month. They might see one estimate value in the email itself, but once they click into the email, go to the website or to the app, they might see a different value. And this causes confusion for them because they see two different values, it's inconsistent, and this is not good. Second issue we see, this introduced an unclear ownership among feature teams. More specifically, when it comes to the implementation of adding a cache layer, we'll be asking ourselves, which team should be taking on this challenge? Should every team just have their own cache implementation? That sounds like duplicate work, as well as a lot of debugging pain in the future. So our first step, before even adding a cache layer, is to consolidate all of the code paths and introduce a middle layer called estimate service in between the individual services and the estimate API. So the estimate service provides a very simple API, only takes in a property ID. Now we have also defined a clear ownership on which team will take on this work, which is owner engagement. And now we're ready to roll up our sleeves and resume the caching work. So before I show you more diagrams, I'm going to spend a minute talking about goals. You might be wondering why. Because it is a good software engineering practice. Without a clear goal, you may not be optimizing your time working on the right problem. So our first goal is to improve performance. You'll be like, yeah, sure, everybody wants cache to improve their performance. But more specifically, we would like to cut down our network round trip to the AWS, as well as some of the database costs. Our second goal is to reduce our AWS bill, because Amazon API Gateway is not free. It is charged by the number of calls you make, as well as the amount of data transferred out. The third, we would like to serve consistent and accurate data. So here we define consistency as all products should return the same estimate value for a given home at a given time. And as far as accuracy, the more stale a piece of data is, we consider it to be less accurate, which means we would like to serve near real-time data. Now let's take a look at our first proposal, which is pretty straightforward. We naturally fitted a Redis cache in between the estimate service as well as the estimate API. In terms of data we store in the cache, we use property ID as our key, and the value is the corresponding estimate value for the home. We thought we were done. But are we? Well, before we call it good, let's take another look at our goals. We said we want to improve performance, more specifically to cut down the network round trip to AWS, as well as some of the database costs. So have we achieved that? Taking another look at our diagram, there's still the database call there. What is it doing? We took a look at what data we're fetching from the database, and turns out that there are certain legal rules we store in the database that decides whether or not a piece of estimate value can be shown to a specific user. Some of these rules comes from local MLS, which stands for multiple listing services. You can think of it as basically an aggregate database where local listing agents upload their listings. And other rules comes from sellers when they suppress the estimate value to be shown on their listings page. But in the end, all of these boils down to one specific value called access level, which controls the accessibility of a piece of data based on a user's role. So you might be wondering, what is the user's role? At Redfin, we define 4 categories for a user: the unregistered, registered, email verified, as well as agents. And naturally, agents can see almost everything. So our second iteration is to also store the access level in the Redis cache. All right, now we get rid of the database because we're down, right? Before popping open the champagne and celebrate, let's take another look at the goals. We said we would like to serve consistent and accurate data. Have we achieved that? Well, someone might have already thought about this. It has something to do with expiration, which is a very common thing when you use Redis as a cache. And as it turns out, housing market is a pretty volatile market. Home prices changes frequently and dramatically. And I believe if you have gone through a home buying or selling process in the past couple of years, you would very well know what that means. So what does this mean for us? For example, say a home price changes every hour or so, and we cache the data for 2 hours. What happens? We end up with stale data. Can we simply cache the data for a very short amount of time, say only 5 seconds? Well, we can, but we'll then be making unnecessary API calls, and which we already know costs us a fortune. How can we strike the perfect balance between cost and benefit? So the way we address this problem is by treating data with different characteristics differently. And the data here we're looking at are properties. We split all of the properties in 2 categories: the active properties that are on the market for sale, as well as off-market properties that are not for sale. We know that active properties or listings, they have a lot of activities going on with them. People go to see the open house, they browse these listings on websites, and also potential home buyers may place an offer. All of these could affect a home price, which means the estimate value for an active listing changes very frequently, and therefore we store them for a shorter TTL. On the contrary, off-market properties, they don't have a lot of things going on with them. Maybe the homeowners will do a remodeling every couple years, but most of the time the estimate or the home prices fluctuates along with the market, so they update less often, and it is fine for these values to live in the cache for slightly longer. And in fact, our estimate algorithm takes these into account as well. So for active properties, we update their estimates at least once a day, even more often for newer listings. But for off-market ones, it updates only once a week. So this is our next iteration. We decide to cache the estimate values for active properties for only 5 minutes, and those for the off-market properties, we're going to cache them for 4 hours. You might ask me, so if the estimate only updates once a week, why can't we cache it for a week instead of only 4 hours? So cache expiration is actually a pretty broad topic, and the answer varies case by case. If you know exactly when the data will be updated, you can cache it for as long as you want until the new information comes, and you just simply overwrites it. But in our case, our side of the system acts on the assumption that it doesn't know the exact time the update happens, so to be on the cautious side, we naturally start experimenting with a shorter TTL to make sure the data is always fresh. Because you never know if a new estimate happens to show up right after you cache the data, right? You don't want your estimate to be 1 week stale. And here comes a very handy Redis command called setEx or setExpire. It both sets the key value pair and sets the key to expire after a given amount of time. This is a very common operation when you use Redis as a cache. So now let's take a look at the result for our single get case. As expected, we observed some perf gain, as well as we achieved a hit rate of about 53%. Remember that we're only caching the active homes for 5 minutes, and for the off-market ones, we're caching it for 4 hours. And here's a graph illustrating the drop in the server response time, and lower means better, if it wasn't immediately clear. We also observed 45% fewer estimate API calls being made on AWS, which means we're saving about 45% on our AWS bill, which is great. All right, so far the setup works pretty well for most of our use cases when you only need one estimate data. What about cases when you need multiple estimate values at once, such as this case? As it turns out, surprisingly or not surprisingly, we did not observe any significant perf gain of our map request. And we are also making similar amount of estimate API calls. What's going on? So we naturally dig deeper into it. And we observed that on the map page, we actually achieved an average of 55% hit rate. However, as it turns out, hit rate doesn't matter as much when you're fetching multiple values at a time, at least when it's only around the 50 range. So to give an example, say we are fetching 100 estimate values at a time, and 50 of them, we retrieve them from the cache. What about the rest of the 45? We're still making a blocking call in our map request to reach out to the AWS client to retrieve these data. So even though we have speed up part of our call by hitting the cache, the entire call didn't improve much because the expensive part, which is network round trip, still exists in the same call, and that is a blocking operation. So as long as that part is still there, we're not going to see too much improvement in perf. And we're not going to observe much on our AWS savings. We then asked ourselves, is it possible for us to eliminate the blocking call at all? And the answer is, yes, we can, if our hit rate is high enough. And now I'm going to introduce Cache Warmup. This is how it works. So when the user is looking at a certain map area, or what we call a viewport, we're going to prefetch the estimate values in the surrounding areas and populate the cache ahead of time with the estimate values in these surrounding areas. To go through an example, say you are searching homes in this map area, or in this box, which is also this orange box in the middle at a more zoomed out level. We first identify all of the neighboring tiles of the orange tile. We then find all of the properties that are not on the market for sale on these neighboring tiles, prefetch the estimate values for those homes, populate them into the Redis cache in a non-blocking background process, a process that is supposed to happen really fast. And our expectation is that when the user later pans around the map and enters any of these neighboring areas, the estimate values for these areas would already exist in the cache, and then there will be no need for us to reach out to AWS to fetch these values again. So it all sounds pretty straightforward. How does our system look like? Remember, this is our previous iteration, which is pretty straightforward. Was the Redis cache sit in the middle between the estimate service and the estimate API? How hard could it be to add a background cache warm-up pipeline? Probably just a couple boxes around it, and maybe we'll fill in the details later, right? As it turns out, this is our current system. And in the middle, the gray box is our cache warm-up pipeline. On the bottom, that's our cache invalidation pipeline. And this looks pretty similar to the previous one, right? Kind of like how you draw now with 2 circles, filling some of the details, and you're done. Anyways, putting that alpha joke aside, let's do a deep dive into the cache warm-up pipeline. So we built that with Kafka and Semza. The reason we chose stream processing to solve this problem is because this problem seems to fit really well with the stream processing paradigm, which says, given a sequence of data, or what we call a stream, a series of operations is applied to each element in the stream. And this needs to be happening in a near real-time fashion. For those of you who aren't exactly familiar with Kafka or Semza, I'm going to give a quick intro without going into too much detail. So Kafka is a distributed streaming framework originally developed by LinkedIn and later open sourced. Redfin adopted Kafka back in 2015 to scale up our fast-growing notification needs. And at the time, it was mainly serving as a low-latency messaging system, and that's where Semza comes into the picture. So Semza is a stream processing framework that uses Kafka for messaging and Hadoop for fault tolerance, resource management, and a bunch of other things. The service promise is that it will provide scalable near real-time event streaming and data processing. This is quite a mouthful. So I have a graph. Shows you the perfect relationship between Semza and Kafka. So each of the boxes in the middle are Semza apps or containers. And a Semza app could subscribe and publish to one or many Kafka topics. And Kafka here mainly serves as a message queue and acts as a buffer between all of the Semza apps. So back in 2015, when we were evaluating multiple similar products to Semza about streaming processing, there are a couple of things stand out that made us choose Semza. And all of them are listed out here, but I will just call out 2 things. The first thing is it comes with an out-of-the-box local storage that is also fault-tolerant. Because the state itself is modeled as a stream, so in case of a machine failure, the state stream will come back in the state before the crash and can be replayed to restore it. So the other thing I will call out is the last item, which says that all of the jobs are decoupled. If any of the job experiences any issue, the rest of the systems are untouched. They're happily running. Redfin, as of today, Redfin has more than 70 plus Semza apps running in prod, processing millions of bytes of content per second. And our usage varies from tracking market activity to sending tour notification and sending listing updates in a timely fashion. We'll also use it for a cache warm-up. Now coming back to our architecture, let's take a closer look at the gray box in the middle, which is our cache warm-up pipeline. It consists of 4 components: the forecaster, request filter, data fetcher, and the data writer. And each of them is a standalone Semza app. The forecaster is responsible for identifying properties on the neighboring tiles and send them to the downstream map. But more specifically, it takes a list of property IDs, finds the bounding box of these IDs, and identify the surrounding boxes of the box I just talked about. Later, for each of the box, it is going to fetch all of the properties that are not currently on the market and send them one by one to the downstream map. The request filter is responsible for validating requests. So what are the things it's validating against? First thing, if the estimate value for a given home already exists in the cache, there's no need for us to fetch it again. They will be filtered out. Second, if a given property, or checking if a given property can display its estimate value at all. So remember earlier I talked about these legal rules we store in the database that decides whether or not we can show a specific piece of data? Yes, that is it. In terms of data fetcher, it's responsible for just fetching the estimate data from API gateway in a batch. And after that, the data writer will be responsible for populating the estimate value into the Redis cache. The reason we made each of these apps as a standalone app is because so that the app will only be responsible for a very specific task and no more than that. And our goal is to complete the entire flow from the request entering the pipeline to the data landing in the cache within 10 seconds. So separating the responsibilities allowed us to achieve maximum horizontal scalability. And you'll probably hear about this buzzword many, many times so far. What does it mean? For example, we know ahead of time that the request filter will have to handle a comparatively larger amount of incoming messages compared to the other apps because the forecaster itself fans out multiple messages for every single message that comes in. So we made it into a single app, gives it 4 times the number of containers, and enabled multi-threading so it can take better advantage of the multiple cores on the hardware. Another example is that for the data fetcher, because it is responsible for fetching things from AWS, and instead of making a request for every single incoming message that we know will break our bank, we utilized a unique feature in Samza called local storage to batch the requests together in order to reduce the amount of costs. Now the cache warm-up pipeline was in place. Once we deployed it, let's take a look at the performance of the multiple fetch case. So first thing we noticed is that we observed a significant bump in our hit rate, more specifically from 55% to 80%. We also observed a huge amount of perf gain. Our P90 dropped from more than 300 milliseconds down to 30 milliseconds, and our median dropped from 60 milliseconds down to 3 milliseconds, almost nothing. And we're also like our batch size, because this is a multiple fetch case, our batch size ranges from 10, 20 to 100, sometimes even 2,000. And we were quite amazed by the performance of Redis in getting multiple values at once. Here's just a graph to illustrate the dropping server response time. The orange line is a P90, and the yellow line is medium. As you could see, notice towards the end of the graph, the yellow line dropped almost down to 0. We also observed 40% fewer estimate API calls for the batch API calls, which means we're on top of the other 45%, we're saving another 40%. Caching validation. So now that we have a fancy asynchronous pipeline running to update the cache, We piggybacked on that and built 2 additional streams to invalidate the cache when estimate visibility changes. And due to the limit of time, so I'm not gonna go into details today, but they were built in a very similar fashion to the cache warmup pipeline. All right, so far everything I talked about seems really good, but we all know when we're doing the development, this is not always the case. What is the catch? The first thing we learned in a hard way is that, it turns out that the supposedly asynchronous process isn't entirely async. There is still one synchronous tissue in the entire link. Because now we're sending messages to the streaming pipeline within the map request, we introduced a system coupling between our web server and the streaming infrastructure. So what happened is that in a recent Kafka upgrade, because of an unexpected bug in the Kafka Python client, some of the nodes in the Kafka cluster, or what we call a Kafka broker, experienced enormous latency in accepting messages, which later trickled down and caused our map request to return really slowly, then further exhausted the resources on the web servers, caused website instability, fire. But fortunately, we were able to shut down the pipeline pretty easily by flipping a feature toggle and later turn it on once the issue was resolved. Whew. The second thing we learned is that as your system gets more and more complicated, it also gets harder to detect issues when there is a fire. So you need to up your game in monitoring. For this feature alone, we built at least 4 different dashboards to monitor the individual parts in our system, including the cache itself, the caching pipeline, the estimate service, as well as the web server endpoints. We're almost done. Let's take a look at what's coming next. The first thing we're going to tackle is we would like to decouple our systems. We're more specifically looking to tweak the Kafka producer config so our broker will time out faster to better isolate the Kafka issues from the web server. Second thing, if you went to the talk given by Daniel Hockman from Lyft yesterday, he introduced an open source project called Envoy that serves as that can serve as a Redis proxy. And we're looking into the possibility of adopting that to migrate our single sharded cache instance to a sharded cluster with the proxy sitting in the front. And lastly, we're continuing to investigating the possibility of increasing hit rate even further by experimenting with TTLs and looking at possibilities to cache more data and further reduce AWS cost. And I am done. Thank you for coming. Do you have any questions? Yes. Sorry, could anybody hand a mic to him? The mic is coming.
Okay, so I was asking, I noticed you use the Redis as mainly as a key value cache. It seems like just like a home ID to like the price.
Mm-hmm.
Did you guys compare using like just Memcache versus Redis?
We have not.
Okay. Okay. Yeah, I was just curious because like Redis, it seems like has all these like data structures, features, but if it's just a simple key value, I was just wondering if there's any other benefit.
Mm-hmm. Yeah, we actually haven't used these advanced data structures yet, because basically we're storing binary value by serializing all of the given objects into a byte stream. And this actually has been serving us really well, at least as a simple cache.
When you were building out the system, it started out, well, like you said, there were multiple iterations. And it started out, although conceptually simple, and you got great specific improvements in the system, it did become a lot more complex in the end. How long did this whole process take from beginning to end? Like, can you give me like an overall timeline? And then also, how big is the team that specifically worked on this estimate thing? And then, did you guys do anything to specifically translate the benefits that you gain into like a business value number?
Okay, so there are 3 questions in total. Hopefully I still remember all of them. The first question is about timeline, right? Okay, it was, I believe it was me and 2 other engineers working on it at the time, and we spent about a month to a month and a half to finish the entire thing. And the second question was about...
What did you guys do to like, before doing it, assign business value to this? Because estimates, getting fast and accurate estimates are valuable to Redfin. Did you like, okay, how valuable? Apparently it was worth 3 engineers and 2 months, right?
That's a very valid question. And we have not measured that yet. But in general, like serving our customers or returning the data faster and handing the values sooner to our customers would always provide a better user experience. And but then it's always hard to evaluate, like to put a money value to these experiences.
Yeah, definitely. I was just wondering if there was somebody decided that this was worth doing.
Yeah, but also more specifically, we're also looking at our AWS bills, which is a more measurable number. Yes.
All right, thanks.
Yeah, thank you.
Hi. So in one of your previous slide, I saw a rate limiting being mentioned. And if I understand correctly, you guys are using Redis to rate limit. So if that is correct, then I'm just trying to understand for unbounded key space, how do you use Redis? Do you use like probabilistic approach to rate limit, or if?
Oh, sorry, do you mind speaking up a little bit?
Yeah, so
it's
the question...
a bit hard to hear.
Yeah, sorry.
Yeah, thank you.
So the question is related to rate limiting. I saw you mentioned rate limiting in one of your previous slide. And is the understanding that you use Redis to rate limit correct?
Use Redis to...
Rate limit.
Oh, you mean like the rate limiting tool?
Yeah. So are you guys using Redis to do your rate limiting?
Yeah, to do rate limiting, yes.
Yeah, so the question is, for rate limiting, I mean, as I understand, you're talking about unbounded key space. So how are you guys doing rate limiting using Redis, where you're talking about bounded memory? Are you using any probabilistic approaches to solving that problem?
I have not looked into that problem specifically, but I could definitely find a better answer to get back to you later.
Okay, sure.
Yeah.
No problems.
Thanks for the presentation. Quick question on your architecture. You said one of the major goals was to reduce the AWS cost, but looks like a part of your application, or like the most part of the application, is like on-prem and just the services on AWS. Is there any reason for that kind of on-prem AWS solution?
Yeah, so just to go back to one of these slides. In the beginning, all the way back. Yeah, say use this as an example. Part of our system is in AWS, and most of the system, even in this graph, is in a self-hosted colo. So the reason is, the reason's actually pretty complicated, but mostly like our estimate algorithm, which computes the estimate value, that pipeline runs in AWS to take better advantage of the resources there. And the value itself is stored up there, and that's why all of our services are trying to reach out to AWS through API gateway to fetch the value.
And a follow-up question is, once you introduce the cache warmup, you said that it reduced 40% the AWS calls. Right?
It's 40% fewer AWS cost.
So how would it it would be like a prefetch, right? So still it would be a call to AWS and then dumps it into Redis. So how do you, I'm not able to understand how there was a reduction in AWS costs.
Yeah, because the reduction is, well, in the previous world, when a user comes to the map page, when they zoom in enough, every time they move the map page around, we're making a request to the AWS. But later, but in the later version, we're not doing that anymore. We are grouping these requests together through the Kafka pipeline and batch the requests, batch all of these multiple ones together and only make one fetch from AWS. So that's where the reduction comes from.
Okay, thank you.
Yeah.
I've got a follow-up question on the same topic. Okay. So the first three boxes are your on-prem here, and the fourth one is the only thing that's on AWS. Is that how I should read it?
So the only thing in this graph, the only thing that lives in AWS is the estimate service API gateway.
Okay. Yeah. I was just wondering if you had to choose the Elastic Cache instead of using Redis here.
You mean like the Amazon hosted Elastic Cache?
Yes.
Yeah, I actually just learned about it yesterday, and we're definitely gonna look into it as a possibility.
Okay. Another question is about the cost. You showed the picture of the cost reduction from the AWS side. What was the cost you incurred in actually having the hardware in on-prem plus operating it, the CapEx and OpEx for this service? Oh,
so you're asking about the trade-offs?
Yes.
Yeah. So the hardware, I would say most of our hardware is already there, and we're not actually introducing any new hardware. In terms of the operating cost, I would say Redis has been very stable so far. We also have automatic failover hosted using Redis Sentinel. So in case something happens, the master would be demoted and the replica will be auto-promoted to be the new master.
Okay, thanks.
Yeah.
Hi, thanks for the good talk. So I understand you guys use Apache SAMSA as a stream processing framework. Is there a reason why you just don't use the Kafka stream directly? I don't know much about SAMSA, so I'm not sure whether it's a valid question.
Well, this is actually a very good question. The reason is that back in 2015, when we were evaluating a streaming processing framework, Kafka Stream was still in its very, very early days. And we're like, maybe not. We need something more stable and more proven. So.
Okay, that's fair. Thanks.
Yeah.
You mentioned about segmenting the listings into active and off market in order to help like define a TTL. Have you guys played with different segmenting rules? Like for instance, since you mentioned the map view, like things in the same region, or I don't know, like by postal code, I don't know, whatever, other ways of segmenting listings that may help with.
We definitely have thoughts about this, and we're actively investigating different ways of caching, especially things on the map. But this is all like future work and yet to come.
Any other questions?
All right. I thought I'm done.
This will be the last question.
Okay.
This would be a simple question too.
Okay.
So what is the volume of transactions you serve through the system?
The volumes? In which specific system were you talking about? Was it the cache or the pipe?
No, in general, like whatever the use case you presented here, the Redfin maps and the page views. So what is the volume or what is the load you take with the system?
I'm not exactly sure if I can share the exact number, but I think it's like 3 digits per second. Does that work? Okay. Yeah, thank you. Okay. I think I am done. You're done. Thank you, everybody, for coming.